want to expand our understanding of one-dimensional motion and use the same concepts that we had used there to describe two-dimensional motion. So in the past, we said that delta x was a displacement vector which would point from xi to xf. Now we're going to do the same idea in two dimensions, but delta r will be the letters we use. And delta r is a displacement vector which points from Ri to Rf. But the same formula from the past still holds. An initial position plus a displacement equals the final position. You can see an example of this drawn in the unit circle, where an object moves from one point in the circle to another point. Let's take a look at the example in the bottom. It says the dots below represent a few positions of a particle that's moving along a path of motion. The blue line is the path. For each dot, draw the two-dimensional position vector of the particle, so show where it's located. And express each position vector using I hat and j hat notation. Alright, so first let's take this dot over here on the left. In order to draw a position vector, we just need an arrow. Position vectors point from the origin to the particle. And now we want to express that vector using I and j notation. So since the vector goes to the left 4 and up 3, we'll call it negative 4i plus 3j. The x component gets associated with I, and the y component, the vertical, gets associated with j. That's one point where the particle is located, but there's other points too. Let's draw a position vector for the particle when it's located on the y-axis at a later time. Now what's going to be the I and j notation for this position? Notice that our arrow points directly up. It doesn't go to the left and it doesn't go to the right. For that reason, in vector form, it's just going to be 3j. Now let's try this guy. Okay, this one goes over 1 in the x direction, then up 3. So we're talking about 1i, which could just be I plus 3j. Finally, there's one more point to sketch a vector for, and that is going to be 1, 2, 3, 4, 5i plus 3j. They all have a y component of 3. The dots below represent a few positions of a particle along its path of motion. For each dot, draw the two-dimensional position vector of the particle, and then express each position using I and j notation. I'll let you answer this on your own scrap paper for a moment, and then I'll give my answers. So the first point that is marked on the path is down here. And let's count the x squares, 1, 2, 3, 4, and then we'll go down 1, 2, 3, 4, 5. All right, this is 4i minus 5j. 4i minus 5j. The next location would have a position vector that looks like this. We're going over 3 down 2. So 3i minus 2j. Interestingly, when you're located at the origin, we don't have to draw a vector. Instead, what we'll say is that it is the 0 vector, which is 0i plus 0j. Or another way to write that same thing is 0 with a vector over its head. Okay, and then we're located here. That'll give us negative 3I plus 2j. And finally, negative 4I plus 5j. Okay, those are position vectors. They would have the letter r. Next, for each consecutive set of position dots, draw the two-dimensional displacement vector delta r between those positions. And we want to, again, express each displacement vector using ij notation. So we're making a displacement vector here now. We're not going to start at the origin. We're going to start at one of the points and go to a new point. And that will have the letters delta r rather than just r. Now let's see if we can put it in ij notation. We have to start at the tail and then see how far we're going horizontally and in what direction. So 3 units to the left, and 1, 2, 3, 4, 5, 6 units up. So we're looking at negative 3I plus 6j would be a way to describe that displacement. It's all about how far you moved to the right or left, and then how far did you go up or down from your starting point. All right, let's try another one. Okay, we're going to the left 2, up 3. Negative 2I plus 3j. Okay. Negative 2I plus 2j. And finally, negative 3I plus j.